Hey guys, welcome back to my channel. Today we will start a new topic in graph theory, Hamiltonian paths or Hamiltonian cycles. Okay, so let us look at Hamiltonian cycles through a real life situation where the concept of this may be used to solve the problem. Say there is a salesman, okay, and there is a graph of the city where every house and the nodes represent the houses, okay, and edges between them represent the road connectivity. Okay, suppose we have five houses. Okay, I will write H1, H2, then H3, H4, and H5. Okay, now they are all connected. There are paths that connect the houses. These are representing the roads. Okay, so there is a road like this maybe. Okay, okay, we will make all of them connected. Okay, these are the roads between the houses. Okay, so now the question is, the salesman needs to minimize time. The salesman has a target. He wants to visit all the houses and do door to door he has to go, but he wants to finish his target in minimum amount of effort and time. Okay, because he has to reach his goal. He has to go to all the houses, visit all the houses using the shortest road so that he comes back where he started. Like suppose he is starting from H5 from here, he will visit all the houses and he will ensure that he has to cover everything in minimum time. That means he will start from H5. He wants a path such that he visits all the houses and comes back again at the starting point H5. So here the houses should not repeat more than once, and the roads cannot repeat more than once. This is known as a cycle. Yes, let us continue. So, yes, so this might represent the cycle I am representing using the red. He visits H5, H1, H2, H3, H4, and then H5. So this is representing a Hamiltonian cycle where cycle means where you started, you have to come back to the same point. Point should be your end point, and you have to visit all the vertices, visit all houses, and your houses should not repeat. No house repeat. Okay, if your house is not repeating, then obviously the edges will also not repeat, or the roads will also not repeat. Okay, so this is the example of a Hamiltonian cycle. Now the question is, will how do you know if you have a graph of that represents some real world scenario? Can you always tell, how will you tell whether this graph has a Hamiltonian cycle or not? Okay, that is the question. Is there any algorithm or any condition where you can, which you can see and conclude whether this graph, which is a huge graph with so many nodes, so many edges, will it have a Hamiltonian cycle or not? Okay, so there is no such litmus test that tells you whether your graph is Hamiltonian, having a Hamiltonian cycle or not. But there is a sufficient condition, not necessary, but sufficient condition that is true for all for graphs where many edges are there, or we can say the degree of every vertex, the degree of every vertex in the graph is greater than equal to n by 2, then we do have a test that is sufficient to conclude that this graph will have a Hamiltonian cycle, but it is not necessary. That means a graph that does not satisfy this condition can also have a Hamiltonian cycle. Okay. So first, for this proof, Dirac's theorem and Ohm's theorem, first we need two results. We will discuss one of the two results in this video and the second result in the next video. So first result is, if your graph with V as vertices, and for all vertices the degree of every vertex is greater than equal to n by 2, then it will be always connected. This would imply the graph is definitely connected. Graph connected with uh, with with surety you can tell it is connected. It cannot be disconnected. Okay, let us try to prove this. So we will assume that we will prove it using contradiction. We will assume our the every vertex degree is greater than equal to n by 2 and our number of nodes is 100, and degree for all the vertices is greater than equal to uh, n by 2 yani 50. Okay, and we will assume it is disconnected. Okay, it is disconnected. Can it happen? Let us see. So minimum there are two connected components like this, and we have to check all possible distributions or number of nodes the two connected components can have. There we are ensured the degree of every vertex is greater than equal to 50. Suppose the distribution is, first M1 has 60 nodes and M2 connected component has 40 nodes. Okay, 60 plus 40 will make 100. Now, what can be the maximum degree of M1, any vertex in M1? The maximum degree can be, it is connected to all other vertices, so it can be 59. Its degree maximum can be 59, that is greater than 50, so it is okay. But the second you see, the degree of every vertex maximum can be 39, and that is less than 50. So that means we knew that degree of all the vertices has to be greater than equal to 50. So this is a contradiction. Now let us check another possible distribution. Another possible case that the distribution can be, your M1 has exactly 50 vertices and M2 has exactly 50 vertices. Okay. So then what can be the maximum degree over M1? The maximum degree can be equal to of any vertex will be 49, and here also 49. But that is less than 50, so that is a contradiction. There are no more possible cases, because if first one we checked it, if it had more than 50, uh, this is the symmetric case when M2 has more than 50 and M1 has less than 50. So we don't need to prove again for that case. Okay. So we can conclude that if there is a graph where degree of every vertex is greater than equal to half the number of vertices, then it is definitely connected. So hope you like this video. Please share it with your friends, subscribe to my channel, and stay tuned for more discrete math videos. Bye bye.